Okay, start again. Yes.
So to figure out like the up or down thing, do you compare the weight of the object, like the newtons of the object, versus the buoyant force?
Exactly. So now, everybody look at me. We're going to take it one step at a time. The buoyant force is equal to the weight of the water displaced. So I'm going to draw a 10 Newton arrow up. Get that? Now we ask you a question. Great question. If I were to let go of this, what would happen?
10 newtons down.
Well, the earth is pulling down with 10 newtons, and the water is pushing up with 10 newtons. So it would stay right there, and that is floating. I know what you're thinking. You think floating means going to the top. No, floating means I can float here, I can float on the top, I can float down here. But in physics, you're either accelerating upwards, accelerating downwards, or you're floating. You're neutrally buoyant. If you're a scuba diver, you would say it's neutrally buoyant. Okay, so now we move on, and I'll get back to the worksheet in just a minute, okay? We go into a block of iron, a 1 liter block of iron, and yes, the volume of this iron is 1 liter, but the density of iron is 8 times greater than water. 8 times. This density is 8. So if that weighed 1 kilogram, you would have to weigh how much? Not weigh, a mass. If this had a mass of 1 kilogram, you would have a mass of 8 kilograms. I have a mass of 8 kilograms. What's your weight? 80 newtons. So I'm going to draw the weight vector as really big, 80 newtons. But now, the next question. What is the volume of water that this 1 liter of iron is displacing?
1 kilogram.
Well, the volume is 1 liter. What is the mass of the water being displaced? Stay with me, okay? What's the mass of the water being displaced? 1 kilogram. What is the weight of the water being displaced? And what is the buoyant force? And so, I tried to teach this to you yesterday. It doesn't matter what the material is, whether it's dense, not so dense, really not dense, or nothing at all. It doesn't even matter what the material is. If your volume is 1 liter, you will experience 10 newtons of buoyant force, period. And so I have 10 newtons of buoyant force, but I weigh 80. If I were to let go of this object, it's going to accelerate downwards. The net force will be 70 down.
Or 70 newtons going down, right?
That's right.
70?
Okay, now, air has a density of 0.001 grams per cubic centimeter. It's 1,000th of the density of water, isn't it?
Yeah.
So how much would this mass be? If this was 1 kilogram, this would be 1,000th of a kilogram. It wouldn't weigh very much. It wouldn't have much mass at all, would it? Multiply times 10, you get 0.01 newtons. So it's hard for me to draw that arrow, but it's, oops, wait, it goes this way. Sorry, arrow wrong way. A tiny little arrow, it weighs 0.01 newtons. So 0.01 newtons down. But how much buoyant force is it going to experience?
1 or 10 newtons.
All right, what is the weight of the water being displaced? What is the weight of 1 liter of water?
1 kilogram.
That's the mass.
Is it 1?
Wait, we did this. What is the volume of water being displaced? 1 liter. What is the mass of the water being displaced?
1 kilogram.
What's the weight of 1?
10.
Okay, so what's the buoyant force?
10 newtons.
Okay, so now if I let go of this object, I have 10 newtons up, 0.01 newtons down, net force up, and it's going to start accelerating upwards. All right, are you with that? Okay, so now let's try the worksheet. I think after that lesson, and you could watch that video if you want to watch it again, but let's take a look at this. What is the mass of 1 liter of water?
1 kilogram.
What is the weight of 1 liter of water? What is the weight of water displaced by the balloon? Well, I have to read it because it said the balloon was filled with what? So what is the volume of that balloon? Does everybody know that 1,000 cubic centimeters is 1 liter?
Yes.
Okay, is that right? All right. And then it says, what is the weight of the displaced water? Well, it's 1 liter of space. So the weight, 1 liter of water is being displaced. So how much does that weigh? How much does it weigh? 10 newtons. What is the buoyant force in the balloon? Archimedes said the buoyant force equals the weight of the water displaced. Is that right?
Yes.
Okay, now it says here, sketch sketch a pair of vectors onto figure 1. 1 is for the weight of the balloon and with the water in it, and the other is for the buoyant force that acts on it. How do the size and directions of these vectors compare? You should have an arrow drawn, whatever size you drew it, and that should be your weight vector, right? And you should have another arrow drawn on the balloon that's what size? Bigger or smaller or same?
There was a bunch of arrows from the top and then a bunch of arrows.
Okay, I'll look at it, but what is the buoyant force on the balloon? It's going to be the same size, same magnitude, right? And it's going to go up. And then it says here, how do they compare with size and direction? Their magnitudes are the same, but their directions are opposite, aren't they? Or different, opposite. Okay, now we go down here. A thought experiment. Pretend we could remove the water from the balloon and still have it remain the same size, but the inside is nothing. It has nothing in it. What is the mass of the liter of nothing? Nothing.
Nothing.
What is the weight of a liter of nothing?
Nothing.
Nothing. What is the weight of the water displaced?
10 newtons. 'Cause
All right.
it's
And
supposed
what
to
is the
be
buoyant force then? 10 newtons. In which direction will the massless balloon be accelerated? Let's say I have 10 up and nothing down. The net force is up. The acceleration has to be up. What you got? Think you got that? All right. This is real physics. You feeling it? You feeling the physics? Okay. Next one. Assume that the balloon is replaced by 0.5 kilogram piece of wood that has the same volume. Oh, it's a block of wood that's 1 liter. Is that right? Okay. It says here the wood is held submerged. I think they should have put 2 hands on there. They're kind of giving away what might happen. I think they should have held it like this, because aren't they kind of telling you what's going to happen?
But that's not.
But we'll figure it out.
Like that.
What volume of water is being displaced by 1 liter of wood? I know one volume, the 1 liter of water is being displaced, but what's the volume of water being displaced? 1 liter. What is the mass of the water being displaced?
1 kilo.
And what is the weight of the water being displaced?
10 newtons.
And what is the buoyant force?
10 newtons.
Now, so we got that down, don't we?
Yes.
Now we got to do one more. How do you know what's going to happen? All you know is that there's a 10 Newton upward force, right? Buoyant force. But what's the weight? It never does tell you the weight, does it?
Up there.
Sort of. The mass is 0.5 kilograms, so what's the weight? 5 newtons. So the Earth is pulling down with 5 newtons down. The buoyant force is 10 newtons up. What's the net force? 5 newtons up. In which direction will it accelerate? Up. All right. And the last one. Repeat the same questions here, but now we're going to use a 5 kilogram rock. You see how that lesson yesterday helped you with this? I hope it did. Repeat. Now we have a 5 kilogram rock, and question A is, what is the volume? Oh, by the way, it's a 5 kilogram rock, but it has what?
The same volume.
That's important. Okay, so now, what is the volume of water displaced by the rock? 1 liter. What is the mass of the water displaced by the rock?
1 kilogram.
What is the weight of the water displaced by the rock? What is the buoyant force on the rock?
10 newtons.
Okay, so I drew a vector, 10 newtons up, but then it says, what's going to happen if I let go of it? Well, first of all, what's the weight of this rock?
It's 5 kilograms, which means it's 50 newtons.
50 newtons. So if I draw 50 down and there's 10 up, the net force is 40 down, and it's definitely going to accelerate downwards. Do you understand the difference between Archimedes' principle? Archimedes' principle simply tells me what the buoyant force is going to be. But whether you sink or float, called the principle of flotation, means I need to look at, and Jeff said it very well, if I want to know if an object is going to sink or float, I mean sink or rise up, go down, or say where it's at, I need to look at buoyant force and what?
Weight of the object.
Weight of the object. Are you with me with that? Okay, so we got that out of the way. That's probably some of the hardest parts of the chapter. Now I do have some today. It's a little bit harder. But all right. So now I'd like you to open up your book. Yes.
I give you my book in a moment.
Okay. Again, if you don't bring your book, I actually have mine. But if you like to, I don't mind if you write neatly, sort of neatly in the book. I think some of you have a book that the person before you did a good job. They were writing all over it. We had a small help session yesterday after, no, not yesterday. Had to be 2 days ago because you weren't here yesterday. And we talked about this right here, and I think it made sense to them. Why is it that a block of steel, let's say it's iron or steel, it's the same density, a block of iron like that, if I let go of it, it sinks. But a block of iron shaped like this actually doesn't sink at all.
It's because the volume is.
The volume of the steel is the same. Yes?
It's because the air in the boat makes the density of the entire object less, and less than water.
It's true, but if I put a lid on this and I took all the air out, would it still float?
Yeah, because
So
nothing
does it
has
determine,
heavy.
I think when you said the air in here, that's an indirect way of saying what used to be there. What used to be here?
Water,
Water, where is it?
it's not in the boat.
So what did the boat
If
do?
it was in the boat, it wouldn't be a very good
Right,
boat.
you're right. Well, what did the boat do to that water? It displaced it. Okay, hang on, wait. Wait a minute, wait. So I don't want you to think that it's air in the boat that makes battleships float. It's not the air in the boat. Now, what I'm trying to say here is, if you were to make that piece of steel, if you had it shaped like this, it won't be a very good boat. Now, why? Because it weighs this much, but it's only displacing this much water. So you only get this much buoyant force. That makes a bad boat. If I shape it like this, the water, the volume of water displaced is huge. And that gives me a huge buoyant force. And I weigh this much, and the buoyant force is the same. When does a boat become a good boat? When the buoyant force on it equals the what? It's a good boat when the buoyant force equals.
The weight of the boat.
So one of the questions on the test might sound like this. How do you get a 500,000 Newton steel boat to float?
To displace 500,000 Newton of water.
Say it again.
You get a 500,000 Newton weighing boat to float when it displaces 500,000 Newton of water.
Exactly. All I had to do, and I'm not trying to say you can design a ship overnight, but the people who become ship designers, engineers, they have to do all this math, and you have to make sure that the design of your ship will displace 500,000 newtons of water. Now, if you made a boat like this, like a V, it wouldn't be very good, because you would put it in there and it would only displace this much water, and so you'd have a huge weight and a little buoyant force, and then your ship would keep going down. It would keep going down, and then it would displace more water. You get more buoyant force, but weight is still bigger, so it goes down. It goes down. And this ship might not ever float, because you may not, but the shape you put it in, it might not ever displace enough water to equal its weight. And that would be a bad ship. And so when we look over here, this next page, I don't know if this will finally make sense to you. Maybe it will. when I look at those two balls there, they're both, which one of those two balls, the beach ball or the bowling ball, which one is buoyant force greater than weight? Which one is buoyant force greater than weight?
The people.
Neither.
Oh, it's, no, it's, it's,
They're neutrally buoyant.
They are both neutrally buoyant. In which of those cases is the buoyant force greater than the weight? If buoyant force is greater than weight, I see that ball going up. And I don't see it going up, do I? If weight were greater than buoyant force, I'd see the object going down. What's it doing?
says the one.
So you're going to get tricked there if you're not careful, because now here's my question. Next question. Which object has more buoyant force on it? Which one has more buoyant force acting on it?
What did y'all just say?
Now, I'm going to look at your faces before I tell you the answer. Which of those balls has more buoyant force acting on it?
The bowling ball.
All I have to do is say, who's displacing more water? Then he has more buoyant force on it. All right, one more time.
Bowling ball.
You got to make that simple, because, hey, wait, stop. That has to be simple, because if the bowling ball is displacing more water, it has to have more buoyant force on it. Now you're mixing that up with when an object floats or sinks or things like that. It's not the same question. Next question. Why? Why would the bowling ball need to displace so much water before it starts floating?
To act upon its mass. This has so much mass, not weight.
Same thing. We can say that. Because it has a whole lot more weight, doesn't it? You have to displace more water to equal your weight because you weigh more. Look at the beach ball. What's the matter with you? Why are you just a little bit under the water? I don't weigh very much. Good test question. An object put in the water will sink until blank equals blank.
Our displacement equals.
Wait.
No, buoyant force equals the weight.
Yes.
Let's go.
Yes. When buoyant force equals weight. So look at this picture here of the canoe. Canoes are made out of light material. And this canoe, what's the matter with you, canoe? Why are you only displacing this much water?
Because the weight is not as much.
That's right. But now I put a lot of people in there, and they were lucky. They were lucky nobody else came in here. But look how much, why are you displacing so much more water now?
The weight is greater.
The weight is bigger. Which object is buoyant force greater than weight? In which case is buoyant force greater than weight? Neither one. Buoyant force equals weight here. Buoyant force equals weight here. Which one has more buoyant force acting on it? The one that's displacing more water. Now you guys are doing it, the way you learn this is what you're just doing now, okay? Talking about it, asking questions, trying to answer them. Okay, I told the other group 2 days ago that ships are so well known and their design is in a computer, so that, especially they did this in World War I and World War II. They would have people with binoculars, and they had a book, and they said, here's a ship, hey, there's a ship coming across the Atlantic Ocean. What? I don't know. They look at the silhouette. Okay, that's this ship here. That's this design here. Oh yeah? Well, tell me about it. Well, they said that they're carrying food and bandages and stuff like that. Well, this ship says, if you're carrying that kind of stuff, how low in the water should you be riding? Not too low, because all the things you have are pretty lightweight stuff. And they say, wait a minute, Captain, that ship is riding way lower than that. We're going to go board that ship. Oh, we just have food and stuff in there. We're boarding your ship. And what do you find down there? Tanks, ammunition, you know. It's like they actually knew how heavily you were loaded. They knew what your total load would be by seeing where you are in the water.
Oh, if you're flowing more.
If you're floating high, you can't weigh, you don't have a whole lot, you have the weight of the ship, but not much else in there.
Is this like a ship or a sub?
No, it's a ship.
Oh, okay.
Now, we'll do submarines. We're going to do submarines in a minute, just a second here. All right, are you okay with that so far? All right, now, what I'm gonna do is a quick survey. We're gonna go through submarines. So if you have your handout sheet with you, this is gonna be simple now. Okay, now find the picture of the submarine. Okay, so here we go. I'm gonna spend most of my time with this drawing right here. Okay, everybody have it? Let's go over here and yes. You what now?
You put on Google Classroom tomorrow.
Oh, wait, I got one. You don't have the packet? Okay, look over on that desk over there. Okay, hold up. It's actually on the main packet that I gave you.
This is not the right sheet. I don't think.
Okay, I need to get started here, okay, because I don't want to run out of time, Dave. So here we have a submarine. This is called a cross section. Everybody know what a cross section is? It's almost as if you cut it this way and you're looking at a 90-degree angle. It's okay. Here's a cross section of a submarine. Which one is greater? Now, let's say there's a dock, and the people. Here's a dock here, and the people are going to walk on there and get on the submarine. Okay. Which one is greater right now? The submarine's weight or the buoyant force on it?
Equal.
What do you think?
Neutrally buoyant.
What now?
Neutrally buoyant.
It is. See, it's not going up. It's not accelerating up. It's not accelerating down. It has to be no net force. So the weight equals the buoyant force right now. Okay, good. So people get in there, and then the submarine gets, the captain gets an order to dive. I want the submarine to go down. Now, what they do is, here's a cross section. Here's where the people are. They're in here. They're safe in here. With this inner hull, then they have an outer hull. Now, in between here are these areas that are kind of like cavities or holes, you know, like empty spaces. And so the captain says, dive, dive. And what they do is they actually flood the ballast tanks. So if you read this, you'll see the word ballast tanks. Now, why would that make the submarine go down? Let's think about it. What's in there right now? Air. And we're going to replace it with water. And water is about 1,000 times more dense than air.
So the weight would.
There we go. So now, you took something that was not very dense, you put something 1,000 times more dense in its place, and now the weight becomes greater than the buoyant force. And now the submarine will go down. Now, it's also true, it's a little bit more sophisticated than just a little can going up and down. They can actually flood the forward ballast tanks first. The second one, they can actually, if they wanted to, they could go down and then start going this way. They could go dive down. They could go down head nose first. They even have ways of steering the submarine. You could go down and steer the submarine and go left and right. That didn't even count the motor. I'm not including the engine. Okay, yes.
Is it like two separate things to like lean into each side?
Yeah, on each side, huh? And they have some in the front, they have some in the middle, they have some in the back.
Do they just like?
They could flood them all. They could flood them all at the same time. Let's say you had an emergency dive. I got to get out of here as fast as I can. I could see flooding all of them at the same time, just go boom, 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 like that.
Is it just two?
Well, it's all the way along the ships. Now,
is it like all the way along?
you know, that's a great question. I'm not a submarine engineer, so I've never designed a submarine, but I'd have to look up submarines from World War II versus today's modern submarines. I'm sure they have some new designs that I don't know about, but it's still the same idea. Now you're down at the bottom, and they said, well, we've down here for 2 days, and, you know, we need to go back up. And he said, well, I overslept that day, and I only know how to go down. I don't know how to make the submarine go up. And that's a problem. But here's what they're going to do. What they're going to do is, Captain, somehow we have to have buoyant force equal to weight. We got to get rid of some weight. Well, let's open up the, let's open up the ballast tanks doors again. But Captain, there's water in there already. If you open them up, there's water outside and inside, nothing's gonna happen. So
is
we
that
have a problem.
vacuum? Did it make a vacuum in there?
But how? If you take the water out of the ballast tanks, where are you gonna put it? Okay, now, so let's take this here, ready? When they were up here, there were a lot of motors running. And these motors were taking air and compressing it into a large number of compressed air tanks. And they took that with them. That was
So
the
they
good
have a
news.
limited amount of
So now,
plastic.
when they get down the bottom, instead of flooding the ballast tanks, they're gonna blow the ballast tanks. Now what they're gonna do down here, they're gonna pump compressed air in there, and if compressed air says, get out of here, water, get out of here. And it's gonna push the water out and replace it with air. Now that space is 1,000 times less heavy than it used to be, and then buoyant force will be greater than weight. And again, you can go straight up, or I've even seen them, I've seen them in the North Pole. I don't know if you know this, but the North Pole has no land around it. It's got solid ice, but no land. South Pole has a continent. There's a real continent with snow on top of it. So you can go to the North Pole and break through the ice. And they actually have submarines that can do it. They go like this, and they can break through the ice. You can't do that in South Pole, I mean, if it's ice, where there's an actual continent with the mountain ranges and everything in the South Pole. A lot of people don't know that. Because they see people walking on the North Pole, but you're not walking, there's no land underneath you. It's all frozen water.
It's more.
Okay, one quick question, I gotta go. Yeah.
So is there a limited amount of times that they can go up then?
Okay, good, excellent question.
Yes.
Again, I'm not an engineer of submarines, but the lower I go down, the more compressed air I'm gonna have to use to try to get that water out, because there's a lot of water pressure out there, isn't it? So that's a problem. I may have to compress the air even more to get that water out. Next, I better have filled all of those air tanks, and somebody better have engineered those air tanks to make sure I have plenty of air. And hopefully, when I get up to the top, I'll hopefully have time to maybe take on some more air, just in case. In times of war, I could see this could be a problem, you know? We had an emergency dive, and it'd stay down there. Now I gotta get up, and I don't think anybody's here. Get some air, get some more air. You know, if not, I gotta go down again. You know, so how much extra air? That's a good question. I don't know that. All right, but anyway, this is essentially, you can see where everything we've learned, that's kind of explains how the submarine works. Now what I'm gonna do now is I'm gonna show you some mini versions of a submarine. So let's take a look at this picture right here.
See the submarine that was like a cartel submarine that got caught, and it was like just bags of cocaine, just like. What?
Just making
Is that what you say to your customers at Hungry Thomas? You're like, can I get a fountain?
I don't know, can you drink it fast enough? It's like one of those really food challenges that like restaurants have sometimes.
Yeah.
Oh yeah, this roasted meal food, you can eat it in an hour.
Give yourself a heart attack.
There's a foam Molotov cocktail.
Dude, have a heart attack in a restaurant.
because this is normally when I wake up.
Have a
every
heart
day.
attack and we'll put you on the wall.
You should see your picture of the
That's
wall.
why.
Yeah.
Look at this, like,
Parker,
we can sleep at the same time.
Parker, did you just say this is normal when you wake up on a weekend?
No, this is when I wake up on a weekend, and that's why I've been waking up during the week this week.
Do you wake up at 1 o'clock on a weekend?
You don't?
You don't.
Not one. I'm not two.
It's abnormal to not do that.
I have.
I wake up at 1.
All right, everybody stop, everybody stop. All right, stop. Okay. Now, what I have is, this is called a classic Cartesian diver, okay? So it's called a Cartesian diver, and this is Cartesian diver number 1. Now, I used to have one of these bottles made out of glass. And again, I'm not, I don't know if you know about these kind of bottles, but, and I hate to tell you this lesson. I'm glad you learned a lesson about there's really a continent in the South Pole, but here's another lesson which, maybe it'll teach you. But when you see bottles like this, they even have smaller versions, and see how they're curved? Okay, well, this bottle is happened to, I didn't drink it, but I did find the bottle. And these are liquor bottles, and the liquor bottles, a lot of them have this shape, especially the smaller ones, so that when you put them in your back pocket, they fit right around your butt. Alright, so anyway, so if you see that, you can even buy these fancy little flasks that are made out of metal, and they also have a curve in them, they fit. Anyway, so I'm sorry I had to teach you that lesson, but I used to have one of these made out of glass, and it'll still work with glass, but it got broken one day, so I went to the plastic kind here. So what I have here is Cartesian diver number 1. I want you to think about this. The rubber part here is actually more dense than water. The plastic is more dense than water. The glass is more dense than water. There's a little bit of water in here, and that's equal to the density of water, and yet the thing is floating. Now it's floating only a little bit above the water, so it must be just a little bit less dense than water. Get that? It's a little bit less dense than water. So I take this bottle and I squeeze it. Oops.
Squeeze the glass bottle.
Oh, amen. That was a nice mistake.
Yeah.
Figure it out.
Hang on. Small mistake.
Oh, don't worry if it's half. I got you. Don't worry if it's half full. I got you. I purposely chose to say half full. They had it because scope sensors. Gimme, because the glass half full.
Oh,
and it might be
snapshot.
half full anyway.
I was having trouble there for a second. What's the scope?
It's not a glass half audio, it's a glass half intent.
I suppose next to it, you can tell what noise is happening. Sarah, when you draw.
Put too much work into it.
Buoyancy.
Is that what you really?
The whole time.
Okay, alright, sorry. Hey, I had not adjusted this before you came here, and it's been here all summer, so I didn't change it. Cartesian diver number 1, everything in here is more dense than water, except water, it's the same density. There's also a little bit of air in there, which is less dense than water. The average density must be a little bit less than water, okay? But when I squeeze it, Cartesian diver sinks and goes down. So the question is, what's making it do that?
Oh, the air from the top is pushing down on it.
Let's think about it now.
Dang it.
A guy named Pascal, Pascal's principle says, if you had an enclosed fluid and you try to put pressure on it and try to compress it, you won't be able to compress it. But I'm actually able to affect that diver without touching it. I never really touch it. But when I press on this water, whatever pressure I put on here is distributed in every direction. Every bit of that diver is getting the same pressure I'm putting on that bottle right now. You see that? So that's the first thing, is Pascal's principle. The next thing is, watch this little piece of air right here. And as I squeeze it, only one of these pieces is actually compressible. Air. I take this much air, and my pressure does what to the air? It makes it into a smaller bubble.
Oh.
But that leaves a vacuum. Nature abhors a vacuum. And so what happens? More water enters the submarine. And now the submarine weighs more than it used to, and now it becomes more dense. So how do I do this? By adding more weight to the submarine, right? By squeezing the air, more water came into the bottom. You get that?
That's what I said.
And that's what made the submarine heavy enough, because the weight was greater than the weighted force, like that. Now, if I can pass this around, but I ask you not to tilt it sideways. That's what happened. Don't tilt it sideways. And then I wanna do one more. Go to the next page now. You'll find Cartesian diver number 2. Do I have another, there's another one there?
Is it this
Now,
thing?
what I have is, I have this little capsule here, and I'm gonna have, Jesse, you can come up here, and, you can come up here. And, so, if you don't mind, just kind of face, and don't do anything I tell you to. And, can everybody see both bottles? This is another kind of Cartesian diver, and don't do anything until I ask you to, all right? But when I say 3, you're gonna squeeze the bottle and see if you can get this diver to go down. 1, 2, 3.
Parker's not that hard.
Parker, it's
I
not
got
that
it.
hard.
Come on, Parker. Jessica did it.
Come on, Jessica did it.
I got it.
There you go.
Come on, Parker.
Jessica,
I got
it.
you do it with
One
one
hand.
hand, do it with one hand.
One-handed?
Come on, Parker.
Come on,
You're trying to
boy.
get sideways.
Parker, come
You
on.
a weak boy.
Parker.
Parker.
Just oh, come on.
Wait.
I do it with 2 fingers.
Come on, Jessica.
Oh, okay.
Come on, Jessica.
Come on,
Parker
Jessica.
can do
Yeah,
it.
you
Try
can go
this
dance
one,
with
so I
that one.
can't get it.
Come on, Parker can do it.
All right, so hey, all right, first of all, this is called a discrepant event. Discrepant event is where 2 things look identical and yet they get 2 different results. And so what we have here is a new kind of Cartesian diver. This kind of Cartesian diver is completely enclosed. This had an opening in the bottom so I could take on more water. This cannot. So how does this one work? Look at the drawing and you'll see the plastic it's made of is more dense than water. The little metal BBs in there are more dense than water, but there is a little bit of air in there, and that's less dense than water. And I know it's floating a little bit. It must be, the average density must be a little bit smaller than water. So now, I cannot make more water go in. So why would it sink?
Because more water's being added into the
No,
tank.
now Pascal's principle is still true. My pressure here is being exerted on that capsule. So look at the shape. What's the shape of the capsule? Look at the shape. Now this is a ratio thing. That's why it's a little bit harder. Yes?
As you squeeze it, it's squishing the capsule, making the air denser, and it's displacing
Well,
less water than it was.
We really mean it takes up less space.
Yeah.
So when the air takes up less space, then this water here is gonna try to fill in that vacuum by changing it and puckering it in, isn't it? What happens to an object when you, let's talk about densities, mass over volume, right?
Yes.
The mass of that object is not changing, but what is changing?
The volume.
So what happens to any ratio? The mass stays the same, but the volume gets smaller.
Less dense.
The density,
More dense. More
now
dense.
it becomes more dense than the water.
Crazy.
And when I let go of it, the air inside there expands, and now the volume gets bigger. So this one's where I add more weight to the submarine. This one isn't changing the volume, and both of them are Cartesian divers. Now you might want to know why was one easier than the other. Okay, I need this to be more dense than that liquid. This liquid though is rubbing alcohol. The rubbing alcohol has a density only about 0.7. So I just need to be more dense than 0.7. Not too bad. This is water, and you have to get more dense than 1. And you're right, it's very difficult. I can't do it without using 2 hands. And it is very difficult. But anyway, I don't have to change the density too much to make it more dense than 0.7, but I really have to squeeze it to get more dense than 1. All right, now, what I'm gonna do is, the last thing I wanna show you, one more demonstration, then I think I might be about it. And I'm sorry, I thought I had these all ready.
Parker, don't look at me.
Bro, honestly,
Failure.
when I was struggling and I looked over and see you doing the one house for a second, I was like, wait.
This right here is a neat little thing, and I'm gonna go ahead and get it ready. And so what I'm gonna do is, I'm gonna fill it with water, and I have this little plunger here, and I'm gonna put the cork in there, and then what I'm gonna do is squeeze it in there and make the water come out. This thing has lots of little holes in it. The holes are exactly the same size, and they're in every direction. And my question to you is, when I squeeze it, which hole will the water come out the fastest? Remember how I did that one bottle? The pressure, the depth was higher and that kind of thing? So Pascal says, if you have an enclosed fluid, and I do, if you have an enclosed fluid like this, and I do, I'm gonna try to squeeze you into a smaller space. You said, it's not gonna happen. You cannot compress a liquid. But whatever pressure I exert here will be the same pressure here, and here, and here, and here, and here. Theoretically, what should happen? Should the pressure in this hole be bigger or less than the pressure here? I get that error, I'm gonna get that error. All right, all right, watch. Which hole will make the water come out faster? Ready?
The one, oh my god.
Okay. Were you able to watch it? Okay.
I saw that.
Try
One.
again.
Oh, we're doing.
See why I like it, right?
That's not water.
I didn't see it.
See why I like this, because everybody gets wet. All right, here we go. Where's it going?
That's mine.
Yeah, so anyways, Pascal.
Yeah, I'm pulling on my
It's
leg.
a desktop. Jeffrey, it's the only time it's ever gonna happen.
I was like, that was about to all of them at the same time.
Here's what's gonna happen, I thought I was gonna show you hydraulics today and then review it on Monday. What I'm gonna have to do though is, the last 2 pages on hydraulics, I'm gonna give you a sheet. And, I made it. Did you see, I already gave you a sheet on hydraulics? Oh, here it is. Okay. Now, what I have here, this is the last thing I'm gonna give you. I already know you have homework, you have diagrams and questions. You don't have to do this at all. This is a practice test, and our test is not till Tuesday anyway. If you feel like, I don't wanna do a practice test till Monday night, you can do it. But I have 2 things here, a practice test, and at the bottom, the back, is about hydraulics. It's the mathematics of hydraulics. And so what we'll do is, I'll have to show you that demonstration later. But when you leave today, let's everybody take one of those, and then, what I'd like to do is, since I don't see you on Fridays, if you come back on Monday and say, I tried that last page, and it has an answer sheet with it. And I think I understand hydraulics, or no, I don't understand it at all. Okay, so let's everybody, when you leave today, just take one of these. All right, thank you. All right, you get a break now.
Hey, how bad did you get?
Oh, it's leaking. Got a little, yeah.
We gotta be careful because this is in early waves. I'm trying to get.
I can see your things.
I know. Oh, wow. It's even more wet, that's even worse.
Oh, yeah.
Look at my eyeball.
All over my, all of my papers, all over my handwriting, and all my things. It was funny.
Because exams we want to
So, I wonder. There's, I wonder if like, I could like make like a fake email, like make a Mr. Shillings email, but it's like what year, and then
In my
like,
eyeball.
like a mass email, like.
Right in my eyeball.
And see if you can like.
I was like this. I wasn't expecting it. I thought it was gonna come out at all. I was like, what's gonna happen?
It's called all the basic cases.